Hi everyone and welcome back to PrepFusion. So in this video we will discuss the control system solutions from GATE IN 2025 paper. So these are all memory based questions. Whatever information I got, I will try to solve these questions. Few questions I saw were a bit on the controversial side or on the moderate side, and the data was also incomplete. That's why like there might be few controversies. Okay, so we will solve this question. This question was the first question. This is a very good question. So they have asked us to find the maximum value of n such that the steady state value of y of t is 0. Okay, so how do you find out the steady state value of y of t? By using the final value theorem. So if I apply the final value theorem, so not steady state error, sorry, steady state value, by using the final value theorem of y of s. What is the final value theorem? It says that s into y of s, limit as s tending to 0, this will give me the y of infinity. Correct? This is what you know. So first of all, I have to find out the expression for y of s. If the input, actually here I missed a point, if the input d of t, right, d of t is a unit step. D of t is a unit step. I missed a point to write here. Okay, so d of t will be a unit step. So first let me find out y of s in terms of d of t. So how do I find it out? So I can simply use simple techniques what I have taught in my block diagram reduction technique questions. Okay, so this is y of s, this will come here y of s. Okay, and this y of s will get multiplied, so this will be y of s minus y of s divided by s square. Now these two are getting added, so here, right, at this point what will be the value? The value will be d of s divided by s raised to power n minus y of s divided by s square, and then it is getting multiplied with this, that is 1 by s plus 1. This is equals to y of s itself, y of s. Okay, so what value I get? So this will be d of s divided by s raised to power n equals to y of s s plus 1 plus 1 by s square. So this will be y of s divided by d of s, or d of s can be here only, here itself, no problems. This will be s square divided by s raised to power n into s cube plus s square plus 1. Okay, into d of s. Now your d of s is unit step, so d of t is unit step, so d of s will be 1 by s. Okay, so if your d of s is 1 by s, this will become s divided by s raised to power n into s cube plus s square plus 1. Okay, now the problem lies when you try to apply the final value theorem, because one thing we know that the final value theorem is applicable only for stable systems, but I can see that this is not a stable, this is not stable because one of the coefficient is missing. That's why this is not a proper Hurwitz polynomial. If it's not a proper Hurwitz polynomial, that means the system is not stable. My y of t is unstable. It's unstable. So I cannot apply final value theorem. So, but according to like what I have seen is like they have given NAT. If they have given otherwise, if options are given that it is not possible, then that option will be correct. Okay, because your y of t will never be stable, hence it will never go to 0. Like at steady state, it will never go to 0. So that is from the data what I have got, that is what I think the answer will be. It is unstable. You cannot make y of t equal to 0. No possible values, no valid values of n will make y of t equals to 0 at steady state. This is the first question. Let's move on to the next question. So let's solve this question. Now they are asking which of the controllers cannot stabilize the closed loop system. Which of them cannot stabilize? This is a MSQ. So this is a controller and this is like a OLT, open loop transfer function. So I have to check for each of them, will they be able to stabilize my system or not. So if I check for the first one, that is a PI controller. PI controller transfer function is simply Kp plus Ki divided by S. Okay, Ki divided by S. This is the PI controller, and now what we have to do, we have to simply write the characteristics equation. Characteristic equation is 1 plus g of s into gc of s. So this is the controller and g of s is given as this is a divided by s square minus b square, okay, equals to 0. Now if I rearrange the terms, so s will be common, so this will be s into s square minus b square plus kps plus ki into a equals to 0. So you will observe one thing, that this will be s cube minus s b square. So this will be if I take s common, plus s into kpa plus kpa plus not plus, sorry, minus b square plus kia. Now you can obviously see from here one term is missing, right? One power of s is missing, that is s square. Obviously it is not a Hurwitz polynomial. If it's not a Hurwitz polynomial, of course you cannot stabilize it. So it is not stabilizable. So this first option will be my correct answer. Okay, let's check it for the next option, PD controller. If I check for the PD controller for option B, this will be my I will directly write now, my controller transformation will be Kp plus Kd into S, Kd into S. Okay, so this will be basically what is my controller transformation, that is A divided by s square minus b square equals to 0. Okay, so now I will write this properly. This will be s square minus b square and this will be plus kp into a plus kd, this will be kd into s into a. Okay, so from here, right, what I can observe is all the coefficients are present. Okay, this is s into kd into a plus kpa minus b square. So all the coefficients of are present, so somehow I can choose my values so that I can make this system stable. So this is possible. So this will not be my correct answer. Now let's choose the second and last one. Okay, sorry, third and last one. So proportional controller is again very simple. If I choose proportional controller, okay, proportional controller, if I choose, this will be k 1 plus k into a divided by s square minus b square equals to 0. So this will be simply, this is again not possible, so minus b square ka equals to 0. Again, like coefficient of s is missing, so obviously this cannot make the system stable, so this will be my correct answer. And last option also will be my correct answer. If you see, last option will be also my correct answer, 1 plus ki divided by s into a divided by s square minus b square equals to 0. So this will be s cube minus s b square plus ki a equal to 0. Okay, so again one of the coefficient is missing, that is s square, so hence this also will not be able to stabilize my system. So ACD will be correct for this question. Let's move on to the next question. This question is also very interesting, and I think this question can also go MTA. Why, I will explain. So we have been given a controller and like simple g of s, and you have to find out the angle contribution of this g of s if the closed loop poles lie here and the controller transformation is given here. Okay, so how will you solve this question? So first, what is my transfer function? Okay, my transfer function will be g of s into gc of s divided by 1 plus g of s into gc of s equals to 0. Okay, so now poles lie in this location, so this equation should satisfy that. This equation should be 0 at s equals to this whatever value they have given. So 1 plus g of s into gc of s at s equals to whatever value they have given should be equals to 0, correct? That means if I rewrite this equation, g of s into gc of s equals to minus 1. Now if I take the angle on both sides, now we know if two complex numbers are multiplied, their angles will be added simply. This will be g of s plus angle of gc of s equals to minus 180 degrees. Okay, so now what is the angle of this GC of S? Now where are the poles? If I draw in the pole 0 diagram, what are the location of the poles? So the location of the poles, one is at this right, this second quadrant, another one is at the third quadrant. So angle of these two poles will be different, hence the angle contribution also will be different. But in the like questions, what I remember, the options were something 60 degree, 30 degree, something like this. Okay, something, or 90 degrees, something like these options were there. So the angle contribution will come out to be different. I will just show you how. So let me calculate for the third quadrant. Okay, let me calculate for the third quadrant pole. So I will just, for now, I will put my pole S will be equals to minus 1.5 minus j 27 by 2. Okay, now if I want to calculate the angle, if I want to calculate the angle of this pole, because like this is 1 by s square, right? So what ultimately the angle will be, this is 1 by s square, so ultimately the angle will be minus 2 into whatever the angle contributed by this s square, whatever the angle contributed by this. Okay, I hope you know all this, I will not explain here. So angle contributed in the third quadrant will be simply minus 180 minus of theta. Okay, theta, I hope you know, tan inverse mod of y over mod of x, all these things I have explained in my full course, I will not explain over it. Okay, so this will be minus 180 into minus theta. Theta will be tan inverse mod of y by x. Y is 27 by 2 divided by 3 by 2. Okay, so this will be if my minus 2 gets multiplied, this will be 360 plus 2 into whatever this is. This is root 3, I think. Tan inverse root 3, tan inverse root 3 is 60 degrees. So 2 into 60 degrees. So this will come out to be 120 degrees, because adding 360 and subtracting 360 is the same. Okay, so now if I just calculate the angle contribution, so I have written this equation, right? I have written this equation. So here I will put in, instead of GC of S, 120 degrees. If I put GC of S instead of 120 degrees, G of S will be 180 minus 120, which is equal to 60 degrees, which is correct, which is not incorrect. Okay, this is also was in the option, this is correct. But now if I choose the other pole, this pole, what will be the angle contribution due to the other pole? That is S equals to minus 1.5 plus j 27 by 2. Okay, the angle contribution due to the other pole will be minus 180 plus theta. Okay, this is the angle contribution. I hope you know, that is under root tan inverse under root 3 into minus 2 is of course there. Okay, so this will come out to be minus 120 degrees. Now if I put in the same equation, my angle of G of S will come out to be 180 plus 120 degrees. So this will come out to be 300 degrees. Okay, or I can write as minus 60 degrees. So I'm getting two answers. Obviously, the two like the two location of the two poles are different. They will contribute, like then the angle contributed by G of S will be different. So that's why I feel that question can be MTA here, because this option was not present. So we just have to check on the final question what was the actual question. Okay, now let's move on to the next question. This question is again very simple. You have to find out the how many zeros of G of S lie on the left half plane of the S plane. How many zeros, not poles, how many zeros? So pretty simple. First let me write the numerator. Numerator will be s cube plus 5s square plus, this is 3s plus 2s, so it will be 5s plus 21. This is the numerator, right? Now again I can use the internal and external product. I can use the root. If I use the root, internal product is 25, external product is 21. So obviously internal product is greater than external product, so the all the poles will lie on the left hand side. So all the poles, whatever poles I will get, all will lie on the left hand side. Hence the answer will be 3 in this case. Pretty straightforward, pretty simple question, answer will be 3. But the previous question, right, were a bit tricky. So control, I would say, came a bit tough, and few questions I feel will be MTA. So that's it from my end. If any update, further update I want to give, I will give in the comments below, or you can join our Telegram group for further discussion. Thank you, and I hope to see you in the next video. Until then, happy learning and all the best for your upcoming examinations.